second thing I'm going to show you is I'm going to move a slit through them. This will be like a Shack-Hartman sensor. Does everybody know what a Shack-Hartman sensor is? Does all the students know what a Shack-Hartman sensor is? So let's imagine Shack-Hartman sensors are arrays of micro lenses. If you bring a beam into the lens, so first I'll tell you what, bring it into the lens, normal incidence, you got to focus. If you bring it at an angle, the focus will move. So let's imagine we bring a beam with a complex phase structure on it. And this micro lens sees this phase structure, the focus is over there. This micro lens sees it plane, the focus is where it should be. This micro lens sees it over there. And so if you look at where all these foci are, you know the structure of the phase across the beam. You can't do that with attoseconds or high harmonics directly because you have to have frequency resolve. You need to be able to, you need frequency resolution to do it. So we do this with a slit. It's the same thing as micro lens. We move it around, so it's like having multiple micro lenses. We move it, and we ask, where is the diffracted radiation pattern on our microchannel plate? And that's what I'm going to show you the results of. I won't show you the actual experiment. So here's the far field. There's our detector. Here's the harmonics that come independently. And here are the harmonic radiation. It's done with the second harmonic focus on beam. That's diffracted in the +1 direction. And here's the harmonic radiation reflected in the -1 direction. One focused, one defocused, just like it should be. Fresnel zone plate focuses or defocuses, and it goes either one way or the other. And here I can change the position. I can take the beam from being a converging lens to a diverging lens. In other words, the beam is going out when it hits the jet, or it's coming in when it hits the jet. And so you can see that now I have focusing down here and defocusing out here. So my Fresnel lens works, my zone plate lens works. And here's a full characterization because the Shack-Hartman sensor looks at everything. I can reconstruct everything about the distribution that comes. So there are two diffracted beams. We're only looking at diffracted beams. They're measured 25 centimeters away from the jet, and so you can actually see it project back, so it's approximately 25 centimeters. You can see one beam expands out, it's deflected, one beam is focused. Of course, it has a virtual focus on the other side back here. And here there's a similar behavior. So you can build a lens into the material, and it's just one of the things. You can manipulate these, control the harmonics as they're being created in a general way. Okay, so I think I'm probably at the end. So I want to just give you something to think about. Last time I said go back and calculate. So I want to cover a few things in the next one. I want to go now on the applications of this and that. So first I talked about lasers, measurements, control, and then acceptance and application. So I want to address, is it possible to image orbitals? I'm going to come back to that just in 2 slides, and that will be my last slide. I want to look at molecular dynamics. Many people have brought up to me, you got this gigantic bandwidth of an attosecond pulse. How can you possibly use it to look at anything interesting? Right? It's an interesting question, and it's a good question. I'll show you one way where you can take it from being a disadvantage to being a gigantic advantage, a huge advantage, making a coherent spectroscopy of time-dependent motion of a molecule. That's the second thing I want to do. And the third thing I want to do is say, we can move some of these ideas into solids. Margaret ended her talk by saying, what happens if we go to higher density material and longer wavelength, and we pretty soon have electrons colliding with some neighbor? Well, in solids, you certainly have an electron colliding with the neighbor, but I'll show you that some of the ideas can move into solids, and it allows you, again, to do unique things, measure unique things in solids that you could not otherwise measure. So that's the direction. I want to end with 2 view graphs, if you don't mind. I can take 2 more. One is just an autocorrelator. You can see the image right there. You recognize that this is an autocorrelator. We have a short pulse coming into a beam splitter. We got one of the mirrors on a delay line. the beam is focused into a second harmonic crystal and into a set doubling crystal. Put it up because I wanted to make the statement in the talk. We measure the electric field as a function of time with a nonlinear interferometer. Maybe the autocorrelator isn't as good, but if I change that to a spectrometer, I really measure the electric field, amplitude and phase as a function of time with this. I could equally measure the electric field as a function of space, should I wish to. Mostly we don't, but you could. Just the sheer interferometer. Therefore, we must be able to measure wave functions because the recollision is an interferometer. It's an interferometer I can control, just like this interferometer. If I can measure electric fields, why can't I measure wave functions? So we must be able to measure wave functions, and we must be able to measure the attosecond pulses as they're created. So I want you to think about that. That's the issue. Actually, I'm going to leave it at this point. So before Friday, that's my next talk, my last one. I want you to think about where you stand on measuring orbitals. I'm sure everyone took a first-year chemistry course. One of the first things they tell you when you come across an orbital is that it's intrinsically an unmeasurable thing. It's only a concept, something to help you think about chemistry. It's not real. And you understand why, right? If you think about the electrons in the system, they're interchanging all over the place. There's no electron in an orbital. So it's an intrinsically unmeasurable system. Or is it? Some argue that orbitals are intrinsically unmeasurable. Some say wave functions are cannot be measured, only they're squared. So where do you stand on this? And I'm going to talk about it. So I want you to think about it before we talk about it. Okay. That's it. Okay.
Thank you very much, Paul. We have time for a few questions. I mean, this was a good question, the last one.
I think maybe...
Shall we show of hands?
Yes?
Yeah.
Anyway.
I will also address this question in my talk tomorrow.
Oh, okay.
So it would be interesting to see if you have the same answer.
I thought I was the only one talking about it.
But I'm going to use different techniques.
Are you going to give us the answer before Friday?
So we're
Are
going
you going to
to
give us the answer before Friday?
Did you have something in the back? You had a question.
Well, it's not really a question, but suppose you could measure wave function, would that affect our interpretation of things?
Well, I don't think so. I don't think it's such a... so you're asking me to answer the question. I don't want to tell you what how I maybe it's implicit in this, how I think of it. So maybe even the answer is how, at least the answer I would see, is implicit in the question. Because not everybody asks me such a question. Let's say it's something to say. Yeah.
I guess my other question would be a bit philosophical but important. If you do something that a large part of the community believes is undoable, well, let's just say you do it. In other words, how do you, right, then those people will assume that there's another explanation, right? So I guess the other question would be, are there always two, for anything that you actually do, right, any measurement that you would make, would there always be two plausible explanations or two plausible ways for thinking about it? And then it would seem to me that the community would be divided into people that would say it's doable and it's not doable, but they wouldn't disagree on the result of the experiment. Do you agree with that concept?
I assume that people would not disagree with the result of the experiment, yes. I will hesitate to enter into an interpretation until Friday. Otherwise I free them from thinking about it over the next 2 days, right, or over the next day. I mean, you should think about this. This is an interesting issue. I agree with you that you have to think about what the explanations are. The experiment is clearly real, I think. I mean, maybe you'll find an error, but I don't think so. The experiment that I'm going to describe is real. The interpretation is interpretation, of course. But the experiment is real. The images we create are real.
It would be most interesting if the two of you have different answers.
Well, I'm probably going to present a different technique than Paul will present. I'm going to be talking about electron diffraction.
No, but the question, okay.
Oh, this is not an orbital, that's just the structure. Electron diffraction is nuclear.
Well, you'll see.
Oh, okay.
But, you know, the scientific process is
Actually, I know it. Pardon?
the scientific process is not being right always. I mean, we'd be out of business if we were always right. So the scientific process is, by definition, having competing measurement techniques, having competing interpretations, and muddling our way to a somewhat better
You have a
understanding.
general idea, you find something unexpected, and then you try to figure out what's
Right.
going on, and that's how science advances.
Yeah.
It's much more messy than undergrad had.
I mean, I look at
I
it.
agree with
We've
that.
we've learned to understand, I feel, physics, new nonlinearity in a sense. Learned to manipulate it under some circumstances. There are broader circumstances which we cannot, but under some circumstances we have. And so we should look for those things that we can do uniquely now with this new nonlinear physics that we could not do before. And so this is potentially one. I'm going to tell you potentially something new in solid-state physics. That's how I am. And, but I think intellectually I will stay within this whole idea of extreme nonlinear optics that I have used as the three lectures.
Maybe that's a good, no, you have something?
There will be another surprise on Friday, too. Snow.
No,
You're kidding?
no.
Yes.
No, but you know, if you bring snow, we fire.
I almost
Send them
wore
back
my
to
boots
the
because there was
Send them
no
back
snow
to
in
the
Ottawa.
Boots,
I thought there's no chance I'm going to get snow in Arizona. This is desert.
We've had actually snow at the school in past years, but it's not kind of Boston snow.
I noticed you didn't say this when you invited me to come and speak.
It's kind of a monolayer. Yeah. Well, thank you so much.
Okay, thank you.
So 5 minutes or so to get organized.